When selecting a breaker size for a unit with a data plate specifying both a maximum and a minimum breaker size, the required breaker size should be sized between the minimum and maximum amp values listed. The National Electrical Code, or NEC, requires that the overcurrent protection device, often a circuit breaker, must be rated for the maximum allowable current flow of the circuit it is protecting. If the data plate specifies a maximum breaker size of 40 amps, then the circuit breaker protecting that circuit must not exceed 40 amps. However, the NEC also allows for the use of a circuit breaker rated less than the maximum allowable current, provided that the circuit breaker is also rated for the minimum allowable current specified. So, if the data plate specifies a minimum breaker size of 20 amps, then the circuit breaker can be rated for any value between 20 and 40 amps. In summary, the required breaker size for a unit with a data plate specifying a maximum breaker size of 40 amps and a minimum breaker size of 20 amps must fall within the range of 20 to 40 amps inclusive. This approach provides adequate protection for the equipment while complying with NEC regulations. Determining the appropriate breaker size involves several factors. Firstly, the data plate and the equipment provides crucial information, including the minimum circuit ampacity and the maximum overcurrent protection device size. The minimum circuit ampacity is the continuous current the circuit is expected to carry. The overcurrent protection device, like a circuit breaker, protects the circuit from overloads and short circuits. Secondly, the National Electrical Code, or NEC, provides guidelines for selecting the correct breaker size. NEC Section 210.20 addresses overcurrent protection and states that the overcurrent device must be rated to protect the circuit conductors. NEC Section 240 provides detailed requirements for overcurrent protection. Thirdly, consider the type of load the equipment represents. Continuous loads, which operate for 3 IOs or more at a time, require the overcurrent device to be rated at 125% of the continuous load. For example, if the continuous load is 16 amps, the breaker should be rated at least 20 amps. 16 amps times 1.25 equals 20 amps. Fourthly, conductor ampacity plays a vital role. The breaker size must not exceed the ampacity of the circuit conductors. Use NEC Table 310.16 to determine the allowable ampacity of conductors based on their size and insulation type. Fifthly, motor applications have specific requirements. Motors have inrush currents when starting, which can trip a breaker that is sized too closely to the motor's full load current. NEC Article 430 provides detailed guidelines for motor circuit protection. It often allows for breakers sized higher than the conductor ampacity to accommodate the inrush current. Sixthly, transformer protection is also crucial. Transformers must be protected against overcurrent. NEC Section 450.3 provides specific rules for transformer overcurrent protection based on the transformer's voltage and impedance. Consider a scenario where a heating unit has a data plate specifying a minimum circuit ampacity of 15 amps and a maximum overcurrent protection device size of 20 amps. The unit operates on a 120-volt circuit and is connected with 12 American wire gauge or AUG conductors with type THHN insulation. The heating unit is a continuous load. To determine the correct breaker size, firstly verify the conductor ampacity. According to NEC Table 310.16, 12 AWG THHN conductors have an ampacity of 30 amps, which is adequate for the load. Secondly, the heating unit is a continuous load, so the breaker must be rated at 125% of the continuous load. If the unit draws 15 amps continuously, the breaker must be at least 18.75 amps. Since breakers are not available in that size, use the next standard size up, which is 20 amps. Thirdly, compare the calculated breaker size with the data plate specifications. The data plate specifies a maximum breaker size of 20 amps, and the calculated size is also 20 amps. Therefore, a 20 amps breaker is appropriate. Another example involves a motor rated at 5 horsepower operating on a 240-volt circuit. The motor's full load current rating is 15 amps. The data plate specifies a maximum fuse size of 30 amps. Firstly, determine the conductor size. According to NEC Table 430.22, the conductors must have an ampacity of at least 125% of the motor's full load current. 13 amps times 1.25 equals 18.75 amps. Use 12 AWGTHHN conductors, which have an ampacity of 30 amps, which exceeds the minimum requirement. Secondly, determine the breaker size. NEC section 430.52 allows for an instantaneous strip circuit breaker to be sized up to 800% of the motor's full load current if needed for starting. However, since the data plate specifies a maximum fuse size of 30 amps, the breaker should not exceed this value. In this case, a 30 amps breaker is suitable, providing both overload and short circuit protection. Another consideration is voltage drop. Excessive voltage drop can cause equipment to malfunction and can damage the equipment over time. NEC section 210.19. A1 provides guidelines for voltage drop. The voltage drop should not exceed 3% for branch circuits or 5% for feeders plus branch circuits. To calculate voltage drop, use the following formula: voltage drop equals 2 times K times I times L divided by circular mils, where K is the conductor constant, I is the current in amps, L is the length of the conductor in feet, and circular mils is the area of the conductor. For example, a 120 volt circuit has a 15 amps load and is 100 feet long. The conductors are 12 AWG copper. The conductor constant for copper is 12.9. The circular mils for 12 AWG conductors is 6,530. Voltage drop equals 2 times 12.9 times 15 times 100 divided by 6,530, which equals 5.93 volts. The percentage voltage drop is 5.93 volts divided by 120 volts times 100, which equals 4.94%. This is within the allowable 3% voltage drop for branch circuits. Another factor to consider is ambient temperature. The ampacity of conductors decreases as the ambient temperature increases. NEC Table 310.16 provides ampacity correction factors for different temperatures. For example, if the ambient temperature is 95 degrees Fahrenheit and the conductors are rated for 90 degrees Celsius, use the correction factor of 0.91. If the conductor ampacity is 30 amps, the corrected ampacity is 30 amps times 0.91, which equals 27.3 amps. Another critical aspect is ground fault circuit interrupter, or GFCI, protection. GFCI protection is required in locations where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor areas. NEC section 210.8 provides detailed requirements for GFCI protection. A GFCI device detects ground faults and quickly energizes the circuit, protecting people from electric shock. Arc fault circuit interrupter, or AFSI, protection is also important. AFSIs protect against arc faults, which are dangerous electrical discharges that can cause fires. NEC section 210.12 requires AFSI protection for branch circuits that supply dwelling units. An AFSI device detects arc faults and energizes the circuit, preventing fires. Surge protection is another consideration. Surge protective devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other events. NEC section 230.67 requires surge protection for dwelling units. SPD diverts surge current away from sensitive electronic equipment, preventing damage. Coordination of overcurrent protection devices is essential for reliable electrical system operation. Coordination ensures that the overcurrent device closest to the fault opens first, minimizing the impact on the rest of the system. Selective coordination studies are performed to determine the appropriate settings for overcurrent devices. In summary, selecting the correct breaker size requires careful consideration of the equipment data plate, NEC guidelines, conductor ampacity, voltage drop, ambient temperature, GFCI protection, AFSI protection, surge protection, and coordination of overcurrent protection devices. Following these guidelines ensures a safe and reliable electrical installation. When a data plate provides both minimum and maximum breaker sizes, adhering to that range is paramount. The minimum ensures adequate current flow for the equipment's operation, preventing nuisance tripping from undersized breakers, while the maximum protects the equipment and wiring from overcurrent situations. Staying within this specified range ensures the equipment operates safely and effectively, without risking damage from electrical faults or insufficient power supply. In practical terms, consider an air conditioning unit with a data plate stating a minimum breaker size of 30 amps and a maximum of 40 amps. The selection process would involve firstly assessing the unit's operational current draw, which should fall within the specified range. Secondly, choosing a breaker size that accommodates the unit's starting current, which is typically higher than its running current. Thirdly, ensuring the wiring is appropriately sized for the chosen breaker to prevent overheating and potential fire hazards. Therefore, a 35 amps breaker might be an ideal choice, providing sufficient capacity for the unit's operation while staying within the manufacturer's recommended range. Proper breaker selection also involves understanding the characteristics of different types of breakers. Standard thermal magnetic breakers are commonly used for general-purpose circuits, offering protection against overloads and short circuits. However, for equipment with high inrush currents such as motors and transformers, time delay breakers are often preferred. Time delay breakers allow for brief overloads without tripping, accommodating the inrush current while still providing protection against sustained overloads and short circuits. Moreover, modern electrical systems incorporate advanced breaker technologies such as arc fault circuit interrupters, or RSIs, and ground fault circuit interrupters, or GFCIs. RSIs detect and interrupt arc faults, which are dangerous electrical arcs that can cause fires. GFCIs protect against ground faults, which occur when current leaks to ground, posing a risk of electric shock. These devices enhance electrical safety by providing additional layers of protection against electrical hazards. In the context of industrial and commercial settings, breaker selection becomes even more critical due to the complexity of electrical systems and the potential for high fault currents. Selective coordination, a technique used in these settings, ensures that only the breaker closest to the fault trips, minimizing disruption to the rest of the system. This requires careful selection and coordination of breaker trip curves, allowing for cascading protection that isolates faults effectively. Furthermore, regular maintenance and testing of breakers are essential to ensure their proper functioning. Breakers should be inspected periodically for signs of wear and tear, and their trip mechanisms should be tested to verify they operate within specified parameters. Over time, breakers can degrade due to environmental factors such as humidity and temperature variations, leading to reduced performance and potential failure. In conclusion, proper breaker selection is a multifaceted process that requires a thorough understanding of electrical principles, equipment characteristics, and code requirements. By carefully considering these factors and following best practices, electricians and electrical engineers can ensure the safety and reliability of electrical systems, protecting people and property from electrical hazards.